Before I begin this last problem, I just want to make one comment, which is that we're only giving you a few examples in the notes because optimization is something that's literally in every single subject that calculus gets used for. So statistics, computer design, graphics, animation, physics, chemistry, biology, I mean, they all have optimization problems. And we can't possibly give you an example of every single kind of problem because there's literally infinite. So we're just going to give you a few examples, and you have to kind of use those ideas plus all the geometry and trigonometry and precalculus you've learned to come up with your functions and then go from there. So it's more about the method and relying on your previous knowledge, because I can't give you an example of everything. It's not possible. Okay, so we're going to imagine a flat bottom cylindrical pot with a circular cross section of radius 4, and I'm going to give it some units here. So 4 centimeters. I'm going to throw those in for future. And then you put a spherical marble inside that has a radius 0 less than r, which is less than 4. So it's placed in the bottom of the pot. What is the radius of the marble that requires the most water to cover it completely? Prove your assertions analytically. All right, so let's draw a diagram. And this is going to be kind of a tricky diagram to draw. And let's give some variables. All right, so we want to draw a cylindrical pot. So that seems like, kind of crazy, but you draw it like an oval shape. That's the circle, but you're looking at it from kind of an angle. That's why it looks like that. All right, so you've got a cylinder right here, and it's got a circular cross section. So a cylinder with a circular cross section. The radius on this thing is 4 centimeters. That's never changing. It just is. It's right here that it's 4 centimeters. Okay, but see, inside this pot, I need to put a marble, a spherical marble that has a radius from 0, which is less than r, which is less than 4. So the most it could be is like up against the sides of this pot, and then it could be really teeny tiny. So I'm going to kind of, I don't know, put it in here. And it's sitting on the bottom because it sinks, right? There's a marble. Crazy enough. Now I'm going to color it, I don't know, orange, just to kind of make it pop a little bit. So it's an orange marble, ball bearing, whatever you want to call it. I mean, that's what this is kind of setting up. And then I want to know, what is the radius of this marble? So this marble has its own little radius inside, r. And I want to know what's the radius of that marble that would make it so that the water, that requires the most water to just cover it. Now the water is here, right? So the water fits inside and has its own volume, right? So covering like that. Sorry, I'm looking for a blue marker here. So I'm going to grab one. So here's the water. And the water is around the marble, but of course it's not in the marble, right? But it's all around it. Okay? So I want to know, well, a couple things. I want to know several things. So I want to know the height of this water. How tall is it? So the water has a height, and there's something that we can think about going on with that. And I want to just cover the marble. So the top of that marble touches that water right there. Okay, so let's think about this. I want to know, what is the radius of the marble that requires the most water to cover it completely? That's volume. So when I'm thinking about my objective function, which I'm already starting to think about, my objective function the objective function would be the volume of the water, right? So I want to maximize the volume of the water that would take to cover this marble completely. Okay, so what is that? Well, it's harder to come up with than you might think, because the thing about the water is that water is not in that marbly area. So you have to think about all of this cylinder, the water level on down, that has a volume. And then you want to take away the volume of the marble, pluck it out of there, imagine. And then what would be left would be the water itself. Right? Everybody who's ever been in a bathtub has done this, right? You get out of the bathtub and then all of a sudden the water goes down, right? So there's the total volume, right? That would be marble plus water, marble and water. H2O is water, minus the volume of the marble. Okay, wonderful. Doesn't have any variables, but we can get some because, now let's think about this. The total volume, this is a cylinder. I mean, if you look at this blue thing right here, that's a cylinder. I might not have drawn it perfectly, but it's a cylinder. I just kind of match the top of it, right? Sorry, my pen kept dropped. All right, so it's a cylinder, and the volume of a cylinder, right, because this is a cylinder, and this is a marble. So cylinder total. The volume of cylinder is pi, the radius of that cylinder, squared, times h, minus, right, the volume of the marble is, well, the volume of a marble, well, it's a sphere, so it's pi, 4/3 pi, the radius for the marble, cubed. Which, that's our variable right there. So I can really kind of erase the marble part because we kind of know that's what we decided our R is going to be, because that's the thing that's varying is, right, you can see right here the radius of that marble can go as low as 0 and as high as 4, not inclusive, of course, because if it was a radius of 0, it wouldn't exist as a marble. Now the cylinder, but see, that cylinder is not changing. The radius of the cylinder is 4, so this is really pi times 4 squared h minus 4/3 pi r cubed. Right, there's the r that we're actually looking at. So note r equals the radius of the marble. We'll just put that. That's our variable. So far I have a volume function, but it's a volume function with two variables, h and r. So this is the volume of the water. It's V of HR. I finally have my objective function. It has too many variables, but it works. All right, so now we need to go find a constraint. So that's step 3. So there's one other thing going on here. And it's a little bit hard to see, which is that we want to just cover it, right? Just to cover, cover completely that marble. We want the water to cover the marble. So the water covers, just covers the marble. Now that helps us. And the way it helps us is it helps us know what h is. And here's why. So the radius on a sphere goes from the center to the edge. So if you think of it, you have one radius right here, but you've got another one right here. From the center to the top of the marble, center to the bottom of the marble. You've got 2 radii. That means that the height of the water is the height of the marble, remember, because we're just covering. So I should put just covers. Right? So h equals 2r. Right? The water just covers the marble, and the marble is 2r, i.e. 1 diameter across. Right? So diameter is 2r, so the h is equal to that diameter of that marble. That gives me h equals 2r. That gives me what I can put in right over here for step 4. So I can say, okay, if my h is equal to 2r, then I can use constraint, use that fact to get only one variable, right? Rather than h and r, I only want one variable, r. Okay, so that would make the v of r function, which would be pi, oh, let me just change that. 4 squared is 16, so I'm just going to call it 16 pi times h, but instead of h, I'm going to put 2r minus 4/3 pi r cubed. And we all know, hopefully, 6 times 2 is 32, so it's 32 pi r, take away 4/3 pi r cubed. This is our new volume function. Beautiful. The effective domain is particularly easy on this one because it was given to us in the problem. The effective domain, I'm going to reverse the normal colors that I've been using. I'm going to use orange for this one. 0 is less than r, which is less than 4 centimeters. It was given. It's right here. Right? But it made sense to make my adjective function in blue because we're talking about water. So now my domain is in orange this time. All right, step 6. Step 6 is we need to find the derivative and the first order critical value. So find first derivative and first order critical value, which shouldn't be too difficult because even though there's pi involved, there's no big fractions or logarithms or any of that stuff. So the derivative would be, let's see here, v prime of r, which is 32 pi. Take away, 3 comes down, so it's 4 pi r squared. Okay, so that's done. The critical value, so there's the derivative part. The crit value would be setting it equal to 0. So we're going to take 32 pi minus 4 pi r squared equal to 0, right? Because that'll be where v prime equals 0. Let's see, that would be 4 pi r squared equals 32 pi. I just added the 4 pi r squared to the other side. Divide by 4 pi, divide by 4 pi. R squared equals 8, right? Because 32 divided by 4 is 8. And that means r equals plus or minus the square root of 8, technically, but the negative one's knocked out because we can't have negative anyway. I mean, what would be a marble with negative radius, right? So that's not in the domain. I'll just put negative, not in domain. And that means that the radius is the square root of 8, which is 2 square root of 2 centimeters. There's your critical value right there. All right, step 7, we just need to use calculus. So use calculus to prove min-max, to prove, in this case, it's a max, because it's the most water. Okay, well, this is an easy second derivative, so we're going to use the second derivative method. Second derivative method, for one thing, it's an open interval. The interval is, oh, I should have written it this way. So it's 0, 4, like this, right? So since it's an open interval and the second derivative is easy to find, we're going to use the second derivative. So v double prime of r would be equal to v prime is right here, 32 pi, take away 4 pi r squared. Derivative of constant is 0, so that'd be negative 8 pi r. So v double prime of our critical value, v double prime of 2 square root of 2. I messed that up slightly. Which would be a negative number, right? I don't actually care what number it is, right? All I know is it's negative 8 pi times a positive 2 square root of 2. A negative times a positive is going to make it negative, right? So it's negative. That means that it's concave down, and that means that we have a maximum at, let's see, the radius of the marble equals 2 square root of 2 centimeters. Sorry. And we just proved it because that second derivative was negative. And they did not want to know the volume of the water, if you look. So they only wanted to know the radius of the marble, and we did that. What's the radius of the marble that required the most water to cover it completely, right? You might be thinking, why isn't it a bigger marble? Well, because if the marble gets bigger, it's actually going to squeeze the water away, right? Because the marble will be swelling and filling it up, right? So the water, the most water is needed to cover if it's kind of in between, if it's not fully filling out the full cylinder. And there you have it. If they wanted the volume of the water, which they didn't ask for, you would take 2 square root of 2 and substitute it back into step 4 right here. But they didn't ask for it.